Okay, in this lecture, we will discuss the flash design, and flash is very important technology given the widespread use for it in consumer electronics. Flash design consists of blocks, and those blocks they are basically erased all at once. Flash design has two major operations: erase and um, program. And basically, the erase, what it does is the chip consists of major blocks. And so this is block 0, block 1, for example, block 2, and block 3. And you can erase a entire block completely. Now, the erase for an entire block comes from the fact that the erase circuitry is very expensive. And when you share one erase circuitry for entire block, you are saving area. So we erase an entire block, okay? And uh, and so for example here this for instance is one block, and right here it shows one block, and inside the block I have multiple pages, and the pages is it's very similar to the word concept that for other memories. And for every so in this case I have how many? I have 16 pages or 16 words, and for every bit line, we would like to call it a string. These are the vocabulary for the Flash folks when we have to, kind of use those. And so typically the Flash design uses the NAND implementation because NAND implementation is more compact and saves area and provide cheaper solution. Now, as we said that we erase an entire block, but when we program or we write to a single page or word, if you will. Okay, so typically the whatever charge on the floating gate, right, determines for me the threshold. So a negative threshold or a positive threshold, I can control this through the tunneling process. A negative threshold represents logic 1 in NAND implementation, and a positive threshold represents a logic 0 again because I'm using NAND implementation. Okay. Um, Now, in this case, here's an example where I have this string consists of 16 cells. All these are called them cells or transistors, if you will, and this is because I have 16 pages, right? 16 pages, and in every page I have you can see this is an entire page. I have multiple bits, which each represented with a string. Okay, the string start with a string selection line and ends up with a ground selection line, and in between you have all these word lines coming to activate certain pages. Okay, um, the uh, the number of cells, and let us go to the next page here. One thing important for me in flash design is what's the size of the flash. And the size of the flash is that number of blocks, okay? Because we said that the flash chip typically consists of blocks, block 0, block 1, block 2, block 3, and there could be more. So number of blocks, block times the block size. What's the block size? The block size equals the page size. The page size, which is this. This is the page size, which is the width, times the string size, which is the length, right? Times bits per transistor or bits per cell. And this is by default, it's 1, unless you are told otherwise in the assignment or the exam. And of course, as we said, the page size here, the page size equals number of columns, okay? And the string size equals the number of pages. Okay, so all these they mean the same thing. Okay, now here's an example. You have a flash of 8 blocks. Every block has 16 pages. Each page has 512 bytes or 4K bits. So the flash size equals number of blocks times the page size times the string size times bit per transistor, which is 1, and that leaves you with 64K bytes. Now, here's another example where we have two blocks, number of columns this and string size is that, but we are using 16 levels so that every cell can program 4 bits. And notice that the number of levels, okay, so number of bits per transistor equals log of 2 to the number of levels, okay, number of levels. Okay, so if you have 16, you can program up to 4 bits. So in this case, the page, I'm sorry, the flash size equals the number of blocks, which is 2, times page size, times the string size, times the number of bits per cell or per transistor, and that gives us 4 million bytes. Okay, with that, let's talk about the two most important operation for the flash. The flash has two major operations: erase and program. And erase, basically what it does, it erases an entire block and makes all stored values on the bits of that block to be 1, because it puts all the thresholds to negative values. But the program, what it does, it writes a 0 into the programmed bits. Okay, and we can program a page by page. Okay, as opposed to erase, where we can erase an entire block. Okay, so now the the um, the uh, again, so when we program a logic, because this is a NAND implementation. Basically, in the NAND implementation, a logic one is implemented with negative VT, so you will have the transistor always on. Okay, and logic 0, it is with positive VT. This is whereas we have normal operation. Okay, it depends on the gate, on the voltage applied to the gate. So let's see how we can do the erase operation. Okay, so the cells are erased by applying the body voltage. So let's see if we have, sorry, let's see if we have the block erase operation. The block erase operation happens by occurs by applying the 20 volt, okay, on the substrate, and 0 volt on the gate. And what happened, because we do this, what happened, the uh, so 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 the block is erased by setting all the control to the gates to the ground, as we see right here, and the substrate to 20 volts, as we see right here. And this high voltage across the gate oxide induces this tunneling, which causes electron to flow from the floating gate to the substrate. Okay, and simply, so basically you have this here is the floating gate, and here is basically the electrons, which are right here trapped. So those electrons, if you connect this to 20 volt and this is to 0 volt, those electrons basically they tunnel all the way to the substrate. And the absence of such, what happens, we will have these gates which are erased, you will have negative VT on them, and basically represent 1 in terms of what is the bit value, or what is the information that is being stored at that cell. Now, this is unfortunately is a very slow process. Okay, so the block erase takes in the order of milliseconds, and we know that in milliseconds we can do millions of operations in today's microprocessor. This operation typically is slow and applies to the entire block. Now, for other blocks, so typically when you do erase, so let's say, for example, this is your chip, and you are applying erase in this on this block. What happened to the other blocks? You don't want to erase them. You apply 20 volt on the gates of the transistors of other blocks, so that you inhibit erase. So because now you have 20 volt on the substrate, 20 volt in the gate, and that will not cause the electrons to tunnel from the floating gate all the way to the substrate. And so that's how you inhibit erase for transistors in, or for floating transistors in other block which are not being erased. Okay, so this is the block erase operation. Let's talk about now the programming, which is for a page. Programming is an operation on a page. The erase is an operation on a block. So typically, when we will program to a zero by tunneling electron, it's the opposite. By tunneling electrons onto the floating gate. Once we tunnel electrons onto the floating gate, we raise its voltage. It's no more negative volts, and now it operates in the normal mode instead of always on mode. The programming cannot restore one values, meaning that once you program a transistor to store a zero, by raising its VT, you cannot write a 1, you cannot make its VT negative until you do an erase for the entire block. So you can erase for the entire block, you can write once to the pages, okay, to the page. Entire page is programmed once, okay, and programmed once only. You cannot reprogram it. Now, to program a page, we have the following operations: you program or you inhibit program. Okay, to program a certain page, we can have the individual bits of the page being programmed to zero or not programmed, meaning they stay save 1. They stay at saved value of 1. So program a 0, it means write a 0. Do not program, it means leave the 1 as is, storing a 1. Okay, so in this case, the bit lines are driven with the desired data. So these are if you want to program a 0, you have to drive 0 volt through the bit lines. If you don't want to program, meaning you want to keep a 1 for this, you drive 8 volts through these bit lines. Okay, so as it says right here. Okay, so then the sub threshold is I'm sorry, the substrate is left at ground. Okay, at ground here, as it shows right here, and then the word lines is raised up to 20 volts. Now this 20 volts right here, what it does is in this case of this page, it will cause the electrons to tunnel all the way to the floating gate, okay, raising its voltage. But in this case, because you have these 8 volts on the source and drain, you don't have this tunneling happening. Okay, so no changes of the threshold for. So this gate stayed negative threshold, and therefore not programmed. And this gate we raise its threshold to a positive threshold, and thereby storing a 0. Now, in this operation, the program operation, we need to have the select line turned off, which is at the bottom of the string, and enable the select signal line, string select line. I'm sorry, for the block, it should be turned on, you will see that at the end this will be programmed and this will not be programmed, and here we write a 0 and here we leave it at value of 1. Other pages that we are not programming, what do we do then? Well, other pages we have to inhibit program, and inhibiting program for other pages is achieved by applying 10 volts. Okay, notice that all of them, the substrate is 0. Okay, the substrate is 0. But other pages which are not being programmed, the pages that are being programmed, you apply 20. Other pages which are not being programmed, you apply 10 volts on the gate. Okay, and that way you do not program those or inhibit the programming for those gates. Okay, so that's as far as programming the flash, and we will stop at this point and continue discussion next part. Thank you very much.